Hello, welcome to Tectonics. In this lecture, I'd like to continue the topic of last time, which was flexure of the lithosphere, and look at some more examples of where this is important, in particular to tectonic processes, but we'll also look at some other examples of surface loading, since understanding the way the surface is moving vertically is important for backing out any sort of tectonic interpretations. So last time I looked a bit at this first topic, the bending of the oceanic lithosphere at trenches and subduction zones, and also at the compensation of volcanic islands and seamounts. In this lecture now, I'm going to go through a bit about crustal loading by ice and also flexural rebound during deglaciation, bending of the lithosphere under sedimentary loads, and flexing up of rift margins and passive margin escarpments. And finally, we'll have a look at the bending of the continental lithosphere by mountain belt loads, which is responsible for the formation of foreland basins. So ice loading is a very nice example of surface loading of the lithosphere because the ice sheet forms independent of any other deformation of the lithosphere. So it's very clear that any vertical motions, at least in the neighborhood of a ice sheet that's forming, are due to the weight of that ice sheet. And then as that ice sheet melts during deglaciation, we see a removal of that load, so we should expect, in fact, a rebound of the continental lithosphere, although this might also be complicated by the formation of proglacial lakes, which is, again, a different load. So we're shifting the load from the ice to kind of the peripheral region where these proglacial lakes form. Even more importantly, though, probably these proglacial lakes provide the opportunity to use geomorphology to mark what was the horizontal level of the land, particularly around the shore of these glacial lakes. So the biggest and best example of today is certainly the Antarctic ice sheet. If we look at the topography of Antarctica, both the bedrock and the ice topography, you can see how thick the ice is, but in particular, you can see how low the surface of the continent is. It, in fact, is well below sea level in many places. Which is not really normal for a normal thickness continental crust. And much of this total elevation is thus due to the weight of the ice that's depressing the surface of the Earth here. The same thing happened during the last glacial maximum and many glacial maximums in Europe, where we had a large ice sheet that formed over Fennoscandia, or at least was centered over Fennoscandia and extended down to the south, so that at the maximum extent it was covering northern Europe, much of Great Britain, of the islands of Great Britain, and we had a secondary ice cap then over the Alps, which is roughly here, that was then providing a load on the Alpine region as well. So presumably this load of the ice depressed the surface of the Earth. The ice today is gone. So we are in fact observing now not the depression, but the rebound, at least in the velocity, the vertical velocity or uplift of the surface. Some of that depression is still remaining, though. And particularly if we look at Fennoscandia, the fact that the Gulf of Bothnia, the center of Fennoscandia, is underwater is really showing us where that ice was centered and how deep that depression was. This is actually looking at the horizontal velocities. This is looking at GPS, these arrows, and they're showing that there is a motion away from the center of this depression, which is reflecting the horizontal motion associated with the rebound and the unflexing of the lithosphere to a load that was centered right here. The uplift rate is what's colored in here, and this is also centered on the Gulf of Bothnia, the middle of Sweden and Finland here, and is highest here, and we can see then a gradient in the uplift as we go towards the peripheral regions. These rates are quite high. This is millimeters per year. So these sorts of vertical rates are either higher, at least at the very high end of what we would ever see from a tectonic process. So we're talking about quite high rates, but presumably relatively short-lived, some thousands to tens of thousands of years. The ice here melted approximately 15 to 20,000 years ago. Similarly, for northern Great Britain, we see also uplift rates in these areas which were ice covered, and now we're in the process of rebounding. So how long does this sort of process take? What's controlling the time scale of this uplift? It's controlled by the viscosity of the upper mantle. And this is the elastic rebound of the lithosphere would be instantaneous, but the viscosity of the mantle is viscous enough that it can't flow instantaneously back to reoccupy this area where it's been pushed away. And it's the time scale of this mantle flow then that controls the time scale of the response. Now, to do this properly, one really needs to solve for the three-dimensional flow within the upper mantle after the load of the ice is removed. But we can do things like make approximations, just sort of looking at the time scale of response of a viscous fluid, for example. So if we look at, if we choose to do that, we can then look at the, say, the uplift rate as a function of time. T here is time in terms of a characteristic time scale of relaxation, which is this tau here. And that characteristic relaxation time then is a function of the mantle viscosity mu and the wavelength of the load that's applied. So similar to the elastic flexure we were looking at last time in the last lecture, there is a dependence on this wavelength. If one does this sort of calculation, what we find is that things like the ice loading for something of this sort of wavelength is going, and the viscosity of the upper mantle, which we can estimate, it is going to take something on the order of thousands to tens of thousands of years for this uplift to completely dissipate and restore itself back to normal. North America had the same sort of situation. We had the Laurentide ice sheet that covered much of North America. That also hit a maximum somewhere in the order of 20,000 years ago and subsequently melted. So just as in Europe, we're still seeing the rebound phase of this this loading. And if we look at the vertical velocity, these are the measured vertical velocities across North America. We can see the effects of this unloading process. The northern part of North America, so pretty much all of Canada, parts of the northern United States, is all rebounding. We're seeing, again, very high rates of uplift in this region. Southern North America, this region here at the yellow arrows, is all subsiding. It's all going down today. Why is that? Well, this is the peripheral bulge region of this elastic flexure. So the ice loading, even though it's inducing flow of the mantle and so on, the lithospheric part is remaining elastic and it's flexing. And that flexure then had a peripheral bulge that was uplifted during the ice loading. And today we're seeing the subsidence of that bulge as it goes down because the ice load is now gone. How do we measure or see this sort of thing? Well, we see this through relative sea level change. So here, for example, are a series of strand lines along a beach. This is in Canada. But what we're seeing then is that the land is going up, and as the eustatic sea level is constant for any period of time, it'll form a strand line. And what we're seeing then is a flight of these strand lines from old to young, which is giving us a measure then of the relative sea level change. What do we mean by that? It looks like the sea level's falling here, but of course it's not. What this is we're looking somewhere up in this region here where the land is rising relative to sea level. It looks like the sea level is falling and we get a relative measure. So this, of course, is very important also for the tectonic problem, because this is a sort of vertical marker that we would use to try to infer tectonic processes. Now, in northern Canada, that might not be important, but it shows that any given point on the Earth may have a relative sea level change due to deformation due to the ice loading. And we have to then account for that if we wanted to try to back out any sort of a tectonic vertical motion that was independent of that ice loading. So during this melting phase in the late glacial period, we might still have ice, but as the ice is melting, we also tend to form these large proglacial lakes, either right out in front or due to meltwater a little bit further out, depending on the geography. But these lakes are very common. For example, the Great Lakes of North America are an example of what were essentially proglacial lakes. In this case, the ice was here, even 10,000 years ago or less than that. There was still, the ice front was still coming down here, and this is really the meltwater from that ice, and it's filling the depression that was due to the downward flexing then of the lithosphere out in front of this ice sheet. The expectation is that this whole area is still uplifting then, as the ice is now gone. And it could be that, in fact, these lakes, the Great Lakes, may well drain in another 5 to 10,000 years. If this area uplifts fast enough that it reroutes the water, in fact, it's already draining towards the ocean. But if that gradient gets small enough, it could be that these lakes are completely drained. We can look, though, at things like the preserved shorelines of these lakes, and they give us good information about how much uplift there has been and what that rate of uplift is. So if we look here at, again, this is the Great Lakes, Canada to the north, US to the south. We can look, these in fact are remnants of a larger lake that once covered this entire area. This was called Lake Algonquin. And the Great Lakes are really kind of the remnants of several much larger proglacial lakes. And by mapping the shorelines, we can measure then where the horizontal was. For example, in this figure, this was at 12,000 years ago. So we find these 12,000-year-old beaches. Of course, they have to be dated, mapped, see what the level is. We can see where they are then above some datum, such as the modern sea level. And what we can see is that, in fact, in this case, that there's up to 150, pushing 200 meters of total uplift of these 12,000-year-old beaches. So presumably that would have been very proximal to the ice loading here. And then we can see how that falls off as we move away from the ice load. So this is moving north to south, north to south, south to north here. So the north is the part that's uplifting the most. And we can look at the wavelength of that and try to fit that with a flexural profile and try to infer then what the flexural rigidity of the lithosphere is. So in this case, these are the effective elastic thicknesses, TE. And we can see that these data can be fit by something with an elastic thickness between about 70 and 100 kilometers. Another example of a not quite proglacial, but a meltwater lake. This is quite famous, at least in I lost the title, but at least in the US, this is quite famous. This is the Lake Bonneville out in the western United States. This is now a desert in Utah and Nevada, but you can see these old preserved shorelines like right here across the hills that mark where there was a meltwater lake that was sitting out here. This is a map without a lot of geographic reference, but this is Salt Lake City. This is the Great Salt Lake, which is the last remnant of a larger lake system that was Lake Bonneville that extended all through this region here. So this is a large lake that is now drying up. The Great Salt Lake is salty because it's concentrating the salt as this larger system evaporates. But that loss of water from the Lake Bonneville then is an unloading of the lithosphere. And so there should be a resulting rebound. And in fact, that's exactly what we can see by mapping these shorelines of the old Lake Bonneville. So the shorelines are preserved on the hills and mountains around this lake, all the way around here. Any place you can find it and map it and date it so that we know that we're looking at the same shoreline. Then we can use that as a level indicator and look at the uplift. And that's what's shown here in these contours. These are contours of uplift, or actually, I think these are contours of the elevation of the paleo shoreline, but that's also, since that was horizontal, that is also the uplift. And you can see that it's a large, roughly circular region of uplift. The lake itself was very irregular. So the fact that the uplift pattern and the shorelines are in fact almost circular is a reflection of the elastic flexure of the lithosphere that's then smoothing this unloading function to give us a more regular pattern of uplift. All right, let's move on to another example where flexure is important to the morphology of the Earth's surface. This now is a tectonic process. I want to look a little bit at what happens on the edges of rifts and passive margins. So during extension, if we have this, just look at this picture over here now, or any of these really, let's look at this one. It's a little bit simpler. So if we have extension, that extension involves thinning of the lithosphere, even if it's done by, let's say, a low angle normal fault like this. We're pulling out the this plate relative to this one. The crust here in the center is, in this case, something like a third of the original crust, which is out here. But any sort of extension is going to lead to crustal thinning. Crustal thinning leads to uplift. Now, why do we have a basin then? Well, we have to add the thinning to the isostatic response which is uplift, and the thinning will be larger than the isostatic response. But if we concentrate on this center point for a moment, even with the sediment loading, here there is still a unloading of the lithosphere, and that leads to an upwarping, which you see in the moho here, centered about that unloading due to the crustal thinning. Okay, so we have crustal thinning, unloading, we have sediments loading, but the net effect is still crustal thinning and uplift. And if that is distributed over a wider region by flexure, then we'll get this broad uplift over the entire region with a localized subsidence due to the displacements on one or more normal faults. So now, instead of thinking about what's happening here, what's happening here? As soon as we go across the limit of this normal fault, we're going to experience the uplift due to the flexural rebound or the flexural isostasy, but none of the crustal thinning due to the normal faulting. So this area here is going to have a net uplift, meaning that it's going to have essentially only an uplift. And this then is referred to as rift shoulder uplift. We're on the shoulder of the rift. We're going to now flex up this part of the crust due to the unloading and thinning of the normal faulting. And we're going to have then a kind of bending and warping upward of the edge of the rift basin. Right. So in fact, if we look at the topography of rifts, we find here, for example, the Red Sea. These are all oriented so that the Rift Valley is on the right edge. But if we go from both sides of the Red Sea, Australia, South Africa, Brazil, these are all either modern rifts or old passive margins. But in any case, the rifting and the normal faulting is occurring out here. The rift, however, is a mountain range, or the flank of the rift is a mountain range. And this is in fact going up with respect to, say, the distal plate here, and it's certainly going up with respect to the Rift Valley, which is out here. And this is a kind of flexure. The footwall is being flexed upward in response to this motion. So if we look at some other examples and look at both the gravity, which remember kind of removes the effect of the sediment fill, because this is a Rift Valley, it's going to be well, this area, let's look down here. This is a valley. This is going to be full of sediments, and the gravity will then remove. By looking at the gravity, we lose the. We can see through and see where the basement really is. So thinning of the crust, in this little example, we're looking also at thinning of the mantle, but if we have net uplift, this is looking at some of the rifts in Africa, and we see that we have quite strong uplift of the rift shoulder. Now, in several of these cases, this is asymmetric uplift. One shoulder is uplifted more than the other, and this is reflecting an asymmetry in the structure of the normal faults that are defining the Rift Valley. So some cases, maybe it's symmetric. If we have, two normal faults in a graben, it might be symmetric. But if we have one big normal fault, say a big listric normal fault system, it can be that we have a very asymmetric topographic signal here. Now, the geomorphology of this is rather interesting as well, because if we in fact have this sort of asymmetric structure, we're having uplift on one side, subsidence on the other. That's a good way to localize the drainage system in the region. That is, the water is going to find a water divide that may be very closely related to this rift shoulder. That's the one part that has the most uplift and the least normal fault related topographic destruction. So the water divide very often localizes right along the edge of this rift structure, the rift valley. If there's then subsequent erosion, the highest erosion is going to be on this rift side where we have the steepest topographic gradient. And so that's going to erode and remove material from here, might be deposited out here. That's going to lead to additional unloading. So we not only now have the rift unloading, so in fact the normal fault might in fact be out here, and we're unloading due to the normal fault motion and the crustal thinning, but then we have erosional unloading or denudational unloading on the on land part immediately adjacent to this normal fault. And that can then shift the maximum uplift or the water divide or the escarpment that's associated with this rifting inland relative to say the normal faulting. And we can see that kind of effect particularly well on passive margins, because on a passive margin, the normal faulting has typically stopped some tens of millions of years ago. So here, for example, in India, this is the escarpment, or sorry, this is the passive margin that's associated with the breakup of Africa, Madagascar, and India. So the rift structures are running more or less along the coastline here. But the water divide, the river system, this is a map of the river system. It's colored by a kind of normalized distance. So the red colors and yellow colors are the maximum distance away from the base level, which is the oceans. But what's interesting here is that this is the continental divide for India. And it's only about 50 to 100 kilometers away from the west coast, but hundreds to 1,000 kilometers away from the east coast. So it's highly asymmetric continental divide, and that divide is in fact defining an escarpment or a mountain belt that's referred to as the Western Ghats. It's very high relief on the west side, very low relief in fact on the east side. But this, we would argue, is really marking this rift escarpment that would have started at the coastline at the time of rifting when these normal faults were active. And now it's migrating inland with time to its current position right here. Right. And so, and you can see this in the geomorphology, for example, here, this is just a Google Earth image from the Western Ghats. This is the western side here and the eastern side here. And if you can tell from the image, this is very flat rivers. These are sediment-filled valleys and so on, very kind of meandering rivers that are going now probably 1,000 kilometers to the east coast. Whereas on the west coast, these are steep. This is what we call a rift escarpment, steep, high relief rivers that they come down to a relatively flat plain in the coast then. But there's a lot of relief on this side because this side is eroding. This side is almost not eroding at all, and that's driving this water divide into that direction. And we can for example, build models of this sort of thing. This is a favorite problem for geomorphologists because it's quite dramatic the way this escarpment evolves. This is a numerical model for that erosional process. If you start with a very steep escarpment, say at a rift coastline, it's going to then, with time, this is time going to the right, it's going to erode and migrate backwards with time. Now, what's interesting for us is this problem, looking at this in profile. This square corner here is the initial topography. And with time, then it goes to something like this, and then this, and then this, and then this, and so on. So that this is the water divide, and it's migrating now from left to right. Now, what's interesting here is that as it migrates, it goes up initially, it goes down afterwards, but you can see that there's actually an uplift and a back tilting of this topographic surface. This is due to the erosional unloading of the lithosphere and a flexural response. So the unloading are these fine lines in the back. These are the erosional unloading as a function of time. And that unloading then is driving a flexure of the lithosphere. It's driving an upward flexure, right? So it's going up where the erosion is maximum. And then it has a wavelength that's tapering off due to the flexure and the flexural rigidity of the lithosphere. When you add those two things together, you end up with a profile like this, where you get an additional uplift. This is essentially that back tilting cantilever effect due to the rifting, but it's now enhanced also by erosion along this escarpment. Okay, let's look at the other big tectonic case of flexure, which is the formation of foreland basins. So this is the loading of the lithosphere by crustal thickening that occurs during compressional orogenesis. This is an example from the Himalaya. This is the Himalayan mountain range here. So our classic example of continental collision and mountain building. This is high topography. That high topography has formed by thickening of the crust. That thickening of the crust is going to drive a sinking through isostasy. Yes, the surface is higher due to crustal thickening, but in fact, most of the crust is being pushed down deeper in the mantle in order to form a crustal root. That's what is in fact supporting this high topography. If that isostatic downwarping is flexural, then we have the surrounding area, which is then pushed down by this loading, and we'll actually see subsidence. And that's what we're seeing in these contours here. These colors here now are contours of sediment thickness. This is basin isopachs in kilometers. And what we see is that there's very thick sediment, 5-6 kilometers, immediately proximal to the high Himalaya, to the crustal thickening zone. And that thins then as we move away from the Himalaya. Down here is showing the same thing in gravity. You can see that there's a big gravity anomaly. So again, looking at the basement sediment contact, it's going down and it's going up as we move away from the Himalaya. And if we transform that into a profile, we can see now the Himalaya would be on this side. We can see then that this is again over several hundred kilometers. We can try to fit that by a flexural profile. And we can see that as we get out here, then we're leaving the foreland, going out into some kind of a flexural bulge out here. So this accommodation space for sediment is what we call a foreland basin. If we look at that sort of cartoon form, we have then these components of that orogenic foreland system. We have a orogenic wedge where the crustal thickening is occurring. We have thrusting of that wedge out on top of the downgoing or the under thrusting plate here. And if this acts then as a vertical load, it pushes things down. We'll have a flexural profile here where we'll have a peripheral bulge out here that is then constraining the subsidence region, which defines a foreland basin. That foreland basin is partially occupied by the orogenic belt itself. So if we have a true growing mountain belt, that mountain belt tends to grow outward through thrust faulting and thickening of the crust. So if this part of the system is under thrusting, this part is over thrusting, we have slicing off of the undergoing plate, a downgoing plate, and formation of a fold and thrust belt. That fold and thrust belt tends to be tapered down towards lower topography, lower thickness, higher thickness in the back. And as it's moving and thrusting out into its foreland, it will partially occupy this foredeep that's formed by the flexure of the lithosphere. So this part is all being flexed down. This is thrusting in. It'll fill that depression. And there are places where, in fact, all of these frontal thrusts are, say, underwater, or in this case, under sediment, because they're relatively thin and in this deep depression that's formed by the downward flexure. The rest of the space is either then filled with air, water, or sediment. And if it's filled with sediment, then we have really a foreland basin system like shown here. If this is yellow, we have parts of the sediment even can onlap or cover the frontal wedge. Otherwise, we have a foredeep of undeformed sediments that sits out in the depression in front. We then have a forebulge where the peripheral bulge of the flexure occurs. And in some cases, we might even have what's called the back bulge, or a region of subsidence behind the forebulge. This is quite shallow, so it's very difficult to see, but if it's tectonically very stable, we might see this in the sediment, and that would really let us define this, this flexural profile extremely well. So here's a Google Earth view of exactly these features in the Himalaya. So this is the high Himalaya, and the back is the Tibetan Plateau, which is all very high topography as well. This is the wedge then that defines the Himalayan mountain belt. It's coming down into a zone where we have a combination of sediment deposition and thrusting. So this is what we refer to then as the wedge top depot zone of the foreland. And it's really sort of a mix. It's hard to know which which process wins at any given time, whether it's uplift by thrusting or sediment deposition on the top. But then we come to the proper foredeep, where there's no longer any thrusting. If we come out of this system, then we come out into the forebulge, where there's no accommodation space or deposition, and then out into the stable part of the continental system. So here's just another example of these sorts of profiles that we get as we cross out of the Himalaya into India, showing this at a little bit more regional scale than I did before. Again, this is the Bugey gravity profile, not the topographic profile, but we can see then this is the flexural profile extending out 600-800 kilometers away from the mountain front. Thrusting is occurring up to about here in this case, so this would be the mixed wedge top depot zone, and then the foredeep proper. And we can see that kind of in map view here, and also begin in this case to map out then what is the effective elastic thickness of the continent in order to explain these profiles, to be fit to these profiles. South America, also the Andes, also has a foreland basin. Here it's a little bit different setting because the Andes are forming at least associated with subduction of oceanic plate on this side, the Nazca plate. So the main underthrusting is down on this side. But as the Andes thicken, they begin to form a fold and thrust belt then out on the eastern side of the Andes. So here we have crustal thickening and shortening due to compression of the South American plate. And that results then in vertical loading that is flexing down the South American plate and giving us a foredeep on this side with a fold and thrust belt on this side. And we can see then the topography of this, high topography in the main Andes, but then we have this sub-Andean fold and thrust belt here and a foreland basin out in front of that system here. So the geometry is shown something like this. The profiles, again, looking at the gravity, we can see that there is a very smooth, long wavelength gravity anomaly, and that can then be fit to the flexural profiles. The Appalachian Mountains of the eastern United States are an example of an old orogenic belt with a foreland basin. Here, the orogenesis ended hundreds of millions of years ago. In fact, we have the next part of the Wilson cycle, if you'd like, with the opening of the Atlantic. But we still have this old mountain belt that's preserved along the eastern United States, along this line. That's the Appalachians, and it has a foreland out in the inland part of the system here. And enough of that is still preserved that we can still see that both the sediments that have preserved that and the topography and the flexure of the basement. So again, the setting is sort of something like this. We have a lode somewhere along the east coast. It's a little bit hidden, if you'd like, because we now have superimposed this rifting on top of it. But the load was a maximum somewhere out here. We have then a down flexing of the North American plate. We can then look at the depth to the basement and try to infer a sort of flexural profile. And that's what this is. This is looking then at the gravity, which is reflecting the depth to the basement, and trying then to fit a profile of both the load and then the downward flexing of the basin. So this process, really in any of these foreland basins, is sort of interesting from both the stratigraphy of the basin, but also for the surface deformation, in that we have an active tectonic process and active shortening at the same time that we have this vertical loading. And these two combine then to give us sort of a space-time change in the uplift pattern, which is quite distinctive. So if we have an orogenic wedge, which is growing and it's also propagating out over its foreland, we have a basin that's sitting in here. That whole system is going to be moving with respect to, say, a distal point out here. And as it moves, that means that the load is moving. And as the load moves, then the flexural response has to move. And what we have is then the basin and its forebulge migrating in one direction, away from the orogenic belt with time. So with time, T1 through T4, this forebulge is going to move out, the basin is going to be pushed out, and we're going to see is a kind of migration of everything. Now the forebulge itself will induce erosion. And so as that moves through, we erode some material as you know, until it, the final position is out here. What we're going to do is remove a small amount of material by erosion. That's going to appear, say, in a stratigraphic record as an unconformity. We've eroded something and left an erosional surface, which new sediments are then deposited on top of. The basin itself will also migrate. So what we'll see is sort of a progressive onlap of the basin as it's moving across the foreland out here as well. But there are other features that are fairly general for this sort of a process. In particular, if this is a mountain belt, an orogenic wedge, which is growing in time, the sediment flux will also grow in time. So when it's initially mostly under sea level, there'll be very little erosion. As it grows above sea level, there'll be more and more erosion. That erosion means more and more sediment. And that means that we're going to go from an underfilled 4 deep, something like this, where the sediment is only partially filling the basin, the rest is water, to a overfilled 4 deep, where we have really sediment filling all the way up to the top. And if this will also be reflected then in the say in the facies of the sediment that's deposited. If we have clastic sediment that's deposited in relatively deep water, but it's still sort of tectonic origin, it might be long traveled, that's something like a flysch facies, right? Or typical sort of flysch rocks. And as it fills up and we have more proximal deposition, more high energy and high sediment flux, this is more of a molasse type of deposition. Now, one more sort of quantification of this process that I'd like to show you. And when in the theory of the last lecture, we talked about things like the sinusoidal load and the line load, but those are essentially 1 or 2D, 1D loading scenarios. The more general case is, how does a 2-dimensional plate respond to a point load? So if we have just a single point, like a single vector loaded onto a 2D plate, that deflection is going to have circular symmetry, right? It's going to be radii of subsidence about that point of the loading. And we didn't really talk about that solution before. We took a line load in and out of the plane, which makes a 2-dimensional problem 1-dimensional. But we can also solve this problem for just what is a point load applied to an elastic plate. Now that point load probably represents, something like here it's drawn as a box or here as a cylinder. But if we have, say, in a foreland basin, the 1 point, and could be kind of a circular representation of all the mass in a mountain belt, for example, would then be applied as a load. And we'll get the same sort of elastic response, depending on what that load is. But we haven't calculated that yet. Let's have a look at that. So this has been calculated. We know what that solution is. This is that solution. So we're now in radial coordinates. So that's again deflection W, but it's now a function of the radial distance r away from that load. And what that solution looks like is this. This is P is the load. Here's our usual flexural parameter, alpha, the change in density from above and below the plate. And what we have here now is this kind of funny function. This is called a Kelvin function, KEI sub 0. It's the 0-order Kelvin function, which is a kind of a Bessel function. Right, but it's just a function. It's a function like a sine or a cosine or an exponential, whatever kind of function you want. That means for any given value of r, there is some value of KEI 0 of this order. And in fact, this KEI function looks like this. All right, and I didn't give the reference, but you can look this up in lots of books, and it looks like this. And that looks remarkably like a flexural profile, right? It goes to infinity at 0 because if you have truly a point load, it's going to sink forever. But it goes, but it has a depression and it has sort of a bulging up, and it goes back down to 0 eventually. Then, right? And you can look, as I say, you can look this up. You can look up how to approximate it or how to calculate it. Here, I just pulled out the Kelvin function from Wikipedia. As I say, it's a special kind of Bessel function. You can look it up. There are different ways to write it. What it is it's an exponential function, right? It's something like this with hyperbolic cosines and exponential, but it's a definite integral, meaning you can take all of this and you can integrate it and you'll get one number, right? So anyway, that's something that you just should know that it exists, and we can calculate that. Now, again, this is quite interesting because of this linearity characteristic of flexure that I mentioned earlier. If it's an elastic plate and you know the solution due to one load, you can add a second load or a third load or a fourth load simply by adding up all these solutions. So in fact, what that tells us is that we can take any kind of loading pattern that we would like, say crustal thickness in a mountain belt, and we can break it up into a series of point loads, calculate those, and add them up. And what that will do is give us then lots of sort of interfering effects. We can have, say, one load here with a bulge. It could be a more complicated one if there's a different load over here, different loads that'll add up. It'll turn things like peripheral bulges into circular patterns. Maybe this is better to look at something like this. So here, for example, is the Appalachian foreland system. And in this case, now we have a mountain belt out here, and there are a whole series of kind of domes and basins out here in the foreland. These domes are a little curious. Some of them might have independent causes, like the Michigan Basin out here is a funny circular basin, or the Illinois Basin. But a lot of these domes, you know, kind of have no reason to exist, except that they kind of make up a part of this arch system, which really defines the peripheral bulge of the foreland basin out here. But rather than being a bulge with cylindrical symmetry, it's a series of disconnected domes, and this could be due to some kind of an interference pattern in the loading. But if we know something then about the pattern of crustal thickening, we can begin to put that together and construct a model for this. So here's an attempt, for example, to take one time frame. In this case, this is the upper Ordovician. We'll do this for any kind of time frame if you'd like. But here's an estimate then of the crustal thickening in the mountain belt. And these are just given as integers, but those are numbers of, say, excess crust in kilometers, 246 or something. So the main loading would have been, at this time, would have been here in the north, right, with a little bit of loading now down towards the south. Each of these can be represented as a point load. We can calculate the deflection due to that point load and add them all up, and what we get is a subsidence pattern that looks like this. So this is in feet. It's America, but this is the subsidence pattern then due to this loading. You can see it's kind of an oblong circular pattern, but it's a little bit complex. If you add in things like the sediment loading, then it would be a little bit different as well. This is the observed thickness of sediments of this age. Okay, so this now is a kind of model that's calibrated to these observations, and you can see that this is more or less the pattern. The greatest thickness of sediment was here, proximal to the loading that was occurring here, and it has a somewhat complex pattern that comes out into the foreland like this. So in fact, we do this at different times time periods. Here's the Devonian. We can look at again at the model or the reverse. Here's the observations. Here's the model. At this time, there was thickening mostly here, but more in the south. We can look then at the pattern by simply adding up all those loads, and that gives us a way then to make a prediction of the foreland basin stratigraphy. And the inverse problem is then essentially to take that stratigraphy, that thickness of sediment, and back it up to try to say where was the crustal thickening occurring at any given time within the mountain belt. So this becomes kind of a way of using the stratigraphy to say something about the tectonic processes, their activity, their timing, and their magnitude back somewhere in the distant mountain belt. Okay, thanks much for your attention. That's it for today. We'll have a discussion on Friday and talk about this when we at that point. Bye.